This presentation is about an article that was published in the journal Information Visualization, and it's all about the efficiency of different graphical representations of trees. Now, there are many different ways we can draw a tree. Here's an example of a classical layered diagram. Here's an example of some concentric circles. The root node in this case is in the center. It's labeled R, and its children, A, B, C, surround it. The children of A are D, E, F, and so on. Here's a third example. This is what's called a tree map. Now, in a tree map, the root node corresponds to the outermost rectangle, in this case the Philippines, and it encloses within it its children. So in this case, the children of the root are Luzon, Mindanao, and Visayas, and each of they recursively enclose their own children, which are individual islands. And as is often the case with tree maps, the areas of the nodes are chosen to be proportional to some meaningful quantity. For example, in this case, the areas are chosen to be proportional to geographical areas of the islands and the regions. Here's a fourth example of how we might draw a tree. This is what I like to call an indented outline representation. Now, we'd like some way to compare the efficiency of these representations. So what we'll do is first enclose the drawing or enclose the representation within a unit square. Okay, so this is a 1 by 1 square, and we're going to allow the representation to grow and fill up as much of this square as possible. We're going to simplify things. Instead of considering this particular tree, we will consider an idealized tree that has a constant branching factor. In this case, it's a branching factor of 3. Okay, so every parent node has 3 children. And also, all the leaf nodes are at the same depth. So this is a complete tree. Now again, we want to expand things to fill up as much area as possible. So we'll just let the nodes expand horizontally. And you can imagine each of the nodes has some label or some information on it. But for now, we're just going to show the nodes as rectangles. Now we can calculate various quantities. For example, the total area taken up within the unit square. Okay? Remember that the unit square is 1 by 1 unit. So the total area, which we'll call A, has to be somewhere between 0 and 1. It can't be any bigger than 1. And it turns out, given the assumptions described in the paper, this particular representation has a total area of 1 minus some quantity. And that quantity corresponds to the area that's shaded in with green here. It's the area used for indentation. That area, if we look at how it changes as the tree gets deeper and deeper, well, it turns out to be of the same order as d over b to the d. And b is the branching factor. In this case, it's equal to 3. D is the depth of the tree. So d, the depth, is what we're allowing to grow arbitrarily large. And we find that asymptotically, the area of the green region is of the same order as d over b to the d. Okay? So the total area A actually tends towards 1. That green area tends towards 0. Similarly, we can look at how big an individual leaf node is. And we find that, well, a leaf node, we're going to call that n sub d. Its area, we're going to call A of n sub d. We find that it's of the same order as 1 over b to the d. So it, not surprisingly, tends towards 0 as the tree grows arbitrarily deep. Now, things get more interesting if, instead of considering total area or just the area of the nodes, if we consider what happens with labels. So let's say we take a label and we want to put this label on the root node. So we squeeze it down until it fits within the root node. And then we have some other label we squeeze down to fit within the next node. And then some other label. In this case, the third label is squarish. It has an aspect ratio close to 1. And we see, oh, the third label, we have to squeeze down quite small to fit it within the node. Okay? That's because the nodes are long and skinny. And so squarish labels are not going to fit well within them. A long, skinny label, in contrast, will be able to take up more area. It'll be able to take advantage of more of the area within a node. Let's simplify things again. Let's assume that all the labels have the same aspect ratio, and we're going to call that aspect ratio L. And we have labels of aspect ratio L on all the nodes. From the previous calculations, we have total area A and the area of a leaf node A of n sub d. Now we're going to calculate some new quantities based on these labels. The first one is A sub L, that's the total area of the labels. And the last one is the area of a label on a leaf node, A sub L of N sub D. Now the reason why this is interesting, this last quantity, this corresponds to the size of the smallest labels in the representation. So these are the ones that are going to be the most difficult to read. And we want to examine how quickly they get smaller as the tree gets deeper. So that's this last quantity, A sub L of N sub D. We can calculate the same types of quantities for other representations. For example, let's take our classical layered diagram and enclose it within a unit square. And again, we're going to simplify things. We consider an idealized tree with a constant branching factor, and all the leaf nodes are at the same depth. We find the total area. We can find the area of a leaf node. In this case, we don't need the big theta notation because the exact expression is simple enough already. And again, we're going to consider what happens with labels. So let's take a label, we squeeze it down in size until it fits within a node. Take another label. In this case, let's take a squarish label and see what happens. We squeeze it down, and we find that actually this is the opposite of the previous situation. In this case, the squarish label fits the nodes much better, and it takes up more area than the skinny label that we put on the first node. Okay. So let's put labels of the same aspect ratio on all the nodes. And from the previous calculations, we have total area and the area of leaf nodes. And now we're going to add the total area of the labels, A sub L, and finally the area of the smallest labels, the labels on the leaf nodes. And what we find are that these last two quantities are inversely proportional to L, the aspect ratio of the labels. This is the opposite of what we had in the previous case, where the quantities were proportional to L. Okay, so this again it just reflects the fact that skinny labels in this case don't do so well. They take up less area on the nodes than squarish labels do. Okay, there are sometimes surprises that crop up when we perform this type of analysis and we compare representations. The representation on the left has an area, a total area, that tends towards 1 as the tree gets deeper and deeper. Okay, the representation on the right, in contrast, has a total area that tends towards 0 as the tree gets deeper. So just comparing total area, we might be led to believe that the representation on the left is better. But the story does not end there. If instead of looking at total area, we look at the area of labels, and in particular the area of the smallest labels, the area of the labels on the leaf nodes, we find these two quantities. Okay? And the quantity on the left has a hidden constant inside the big theta. If we peek inside, look at the details, and we can find what that hidden constant is of the leading term, it turns out to be b minus 1 squared over b squared. And that's always going to be less than 1. So that means the area of labels on the leaf nodes on the right is going to be larger. Okay, so when it comes to legibility, the legibility of the smallest labels will be better with the representation on the right. Here's another example of a similar type of surprise. The representation on the left has a total area of 1, and the representation on the right has a total area less than 1. So that would indicate that the representation on the left is better. But if we look instead at the labels, the smallest labels, the labels on the leaf nodes, we find that the labels on the right are bigger. In fact, for a sufficiently deep tree, they're going to be about 10 times bigger in area than the labels on the leaf nodes on the left.